Okay, so we just finished talking about different concentration expressions and equations we can use to talk about the concentration of a solute in a solution. And one of them that chemists use a lot is molarity. And the reason we use molarity so often is because it contains two units that are very valuable to us in solution chemistry. It contains liters of the solution, and it contains the moles of solute dissolved in that liters of solution. So molarity is the units for molarity, big M, are also moles per liter. Because we have two units here, and one of them is the mole, we've seen this before, grams per mole, number of compounds per mole, molar volume, the volume that 1 mole of gas occupies. All of those had two units, and they were used as conversion factors to calculate in and out of the mole. So it turns out that molarity, because it's moles per liter, molarity can be used as a conversion factor. It converts between moles and liters. So if I'm given moles of a compound, a solution, and I need to figure out the liters of solution that I need. So if I know, am given the moles of the solution, or solute, I should say, and I need to figure out from the moles of solute that I need how many liters of solution I need to get, I use molarity. Molarity, which is moles per liter, is a conversion factor that will get me from moles to liters. So moles of solute, remember molarity is moles of solute per liter of solution. So for every 1 liter of solution, I have X moles of my solute. I can set it up this way as a conversion factor to convert or cancel out my moles of solute, and that will give me my liters of solution I need to deliver in order to get that number of moles. I can also go backwards. Instead of, if I have the liters of solution that I have, so I say, I have like 20 liters of this certain concentration solution. If I know the liters of solution, I can very quickly calculate how many moles of solute are in that solution by using molarity, because molarity is moles of solute per liter of solution. So if I have liters of solution here, I can use molarity. X moles of that solute concentration is dissolved in every 1 liter of solution. I can convert from liters of solution to my moles of solute. So I can convert in and out of the mole using molarity. Now I'm going to give you a simple equation to remember. And this is not something that I made up or anything like that. I mean, it's obvious, it's in your book, you've read about it already. But an equation that you're going to need to remember and be able to use from time to time is that molarity times volume in liters equals moles. Because molarity is moles per liter. If you multiply that times liters of solution, don't you get moles out? Yeah. So molarity times volume is going to equal moles. And the volume of the solution will be in liters. So let's see if we can figure out how to do some conversions with molarity as our conversion factor. So the first one says, how many moles of HCl are there in 4.3 liters of a 0.2 molar HCl solution? Now, we're given the molarity here, we're given the volume of the solution, and we're asked for moles of solute. We could use the molarity equation. Molarity equals moles of solute divided by liters of solution, right? We could use that. We could substitute in the 4.3 here. We could substitute in X here for our moles, and the molarity is 0.200 molar, or moles per liter. All right? And we could solve for the moles of HCl. However, I want to do it a different way this time. I want to use molarity as a conversion factor because I'd rather do that problem now to show you how it uses a conversion factor, because we're going to use it in a stoichiometry problem below. All right, so when you think about using molarity as a conversion factor, you're always asked for conversions, what you're given, and what you need to find. So we're given 4.3 liters of our solution. How many moles of HCl are there in 4.3 liters of this HCl solution? So we're given 4.3 liters of solution. The molarity is not a given. Molarity contains 2 units. It's the conversion factor. Always be aware of that when you do a molarity problem. Molarity is the conversion factor, not the given. Alright, so it says how many moles? So I need to convert from liters, so liters on top and bottom here, and I need to convert 2 moles of HCl. Well, that's my molarity. Molarity is moles per liter, and it's 0.200 moles of HCl for every 1 liter of solution. That's how you get a 0.200 molar solution, 0.200 moles for every 1 liter. So if I do the calculation here really quickly, you get your answer. I don't have my calculator out, but you see what the answer is, 4.3 times 0.2. Alright, I'm going to have to get my calculator out. Let's just keep going though, because I don't want to waste our time on our video. Alright, let's look at the next question. It says, how many milliliters of 0.175 molar mercury 2 nitrate is needed to completely precipitate. Wait, that doesn't make any sense. 2.5 grams of potassium iodide. Let's change that to mercury iodide. HgI2. So 2.5 grams of mercury iodide. Why did I say that? Well, in this equation here, we're given an equation. Do you remember whenever you're given an equation with a word problem, you probably have a stoichiometry problem? If you can't remember what a stoichiometry problem is, go back to chapter 9. It's a must. If you are given a chemical equation, you can convert from a quantity of one reagent, like mercury nitrate, to the quantity of another reagent, like mercury 2 iodide, using the mole as your central unit. You're going to go through the mole to convert from one compound quantity to another. That's stoichiometry. Remember doing that now, chapter 9? If you don't, or if you feel like you need a refresher, go back to chapter 9 this week, okay? Because you're going to have some stoichiometry problems still. Remember, this class always builds on itself slowly. So why did I say this has to be mercury 2 iodide? If we look at this chemical equation that's given, it says a solution of mercury 2 nitrate is mixed with a solution of potassium iodide. That's what it means to be aqueous, the water solutions. They make a solution of potassium nitrate plus the solid mercury 2 iodide. In the question, it said that we precipitate out 2.5 grams. The precipitate is the solid, so it must be the mercury 2 iodide. So let's read the question again. It says, how many milliliters of this mercury 2 nitrate solution, so we're going to put that right here, how many milliliters of this solution is needed to completely precipitate 2.50 grams of mercury 2 iodide? Alright, now I'm given another number in this problem, and this is where people get thrown off. It says how many milliliters of this solution, and the solution is 0.175 molar. Notice I'm not writing that underneath but on top. This is our conversion factor. Molarity is moles per liter. So it's going to convert moles of mercury 2 nitrate to liters of mercury 2 nitrate. That is not a given or a known in this problem. Well, it is a known, but it's a conversion factor. All right. So that's our conversion factor. Now, what are we actually given in this problem? We want to precipitate out 2.5 grams of mercury 2 iodide. So that's what we're given. We need to convert from grams of mercury 2 iodide to milliliters of mercury 2 nitrate. How much we need to get that precipitate. Remember that in stoichiometry we always go through the mole. So if I'm given grams of my starting material, I always need to convert that into moles of my given reagent. So I need to convert grams of mercury 2 iodide to moles of mercury 2 iodide first. I will go ahead and give you the molar mass. The molar mass is going to be used to calculate from grams to moles. So the molar mass of mercury 2 iodide is 454.2 grams per mole. And I'm not giving that to you because you can't find it. You could actually just calculate that from the periodic table masses. Alright, once we get the moles of mercury 2 iodide, now we can do our mole to mole conversion and calculate our moles of mercury 2 nitrate. So this is our mole to mole. We went into the mole, and then we did a mole to mole. Remember all this? And now we're going to convert out of the mole. We're going to use molarity to convert from moles to volume. So I'm initially going to convert to liters, and then just simply convert that to milliliters. So I'm actually doing a kind of difficult problem here, because I'm making you do multiple steps. How many conversion factors are we going to have? Well, we're going to do into the mole with molar mass, that's 1. A mole to mole, 2. A mole to liter with molarity, 3. And a liter to milliliter, 4. So we're going to have 4 conversion factors in this problem. Let's set it up. We're given, and that's what we always start with, 2.50 moles of our mercury 2 iodide. We want to convert that, I'm sorry, not moles, grams. Sorry, you're probably like, well, hold up. Grams of mercury 2 iodide. We're going to convert grams to moles using our molar mass, okay, because we want to convert into the mole first. So remember, 1 mole, the molar mass of this compound I gave you, is 454.2 grams for every mole of mercury 2 iodide. Okay, so now I've gotten to moles of mercury 2 iodide. Now I need to convert that to moles of mercury 2 nitrate. In the balanced equation, for every 1 mole of HgI2, mercury 2 iodide, you'll notice the coefficient in front of that number was 1 mole of mercury 2 nitrate. So I've converted from moles of mercury iodide to mercury nitrate. Alright, from there I convert to liters. This is where I use the molarity. Molarity is moles of mercury 2 nitrate to liters of mercury 2 nitrate. The molarity was 0.175 moles of the compound per liter. So for every 1 liter, there's I'm running out of room. So I've already written that. You've probably already written it down, so it's good. Let me write it down again. HgNO3, 2. So for every 0.175 moles of the mercury 2 nitrate, 0.175, I'm sorry, there's 1 liter of solution. That's our molarity. That's the new conversion factor we're using. Now we've converted from moles of mercury 2 nitrate to liters of mercury 2 nitrate. Alright, and then I'm going to come down here, and I've got my last one. We don't want liters of the solution. We were asked to calculate milliliters of solution. So for every 1 liter, that's 1,000 milliliters of the solution. So we have, in your calculator, you're going to put in 2.50 times 1 times 1 times 1 times 1,000, right? That's your entire numerator. In your denominator, you're going to divide by 454.2 times 0.175 times 1 And your unit that's left over, because the liters on top and bottom cancel, is the milliliter. So you'll end up with milliliters as your final. So when you go and you calculate all of that, what will your answer be? It should be, hopefully you'll get this too, approximately, because we're going to round off, 31.4 milliliters of mercury nitrate solution. Mercury 2 nitrate. What does that mean? If you look back at the problem, it says how many milliliters of that solution is needed to react to completely precipitate the product. So if we wanted 2.5 grams of mercury 2 iodide as our product, we would have had to have used 31.4 milliliters of the solution in the reaction to get out that much of the product precipitate. Chemists use these calculations very often. Stoichiometry is very important in the process of developing and calculating, preparing for chemical reactions and product yields. So if you don't remember the stoichiometry part of solution stoichiometry, you need to go back and review chapter 9 in your textbook, Stoichiometry. And all we've done now is we've added one more conversion factor, molarity, which is the same thing as moles of solute over liters of solution. We can convert in and out of the mole using molarity as our conversion factor, from moles of solute to liters of solution. So practice these problems, practice. All right, let's go back here. And we're going to look at dilution for a second. So we've talked about solution stoichiometry. We've done a difficult problem, so the other ones should seem a little bit easier, hopefully. Let's talk now about dilution. What does it mean if I told you to dilute something? Like, oh, that sweet tea is so strong. Could you dilute it for me? If I made sweet tea and I thought it was way too strong, what would you probably do? You'd probably add more water to it, right? And the water's the solvent. When we want to dilute something in chemistry, we add solvent to a concentrated solution to make it more dilute or less concentrated. When you dilute something, the moles of the solute dissolved in that solution don't change. For example, if I have a concentrated solution, like I brew some coffee, and the coffee is very, very concentrated, I need to make my cup bigger. Alright, let's say I have this cup of coffee. And here's the solution I have, and it's very, very, very concentrated. And here's my moles of solute. They're very close together, or highly concentrated in this solution. Lots of moles per liter, right? Alright, if this is a high concentration, if I want to dilute it, do I add more of the solute, or do I add more of the solvent? We said that we add more solvent. Solvent dilutes. What that literally does is if I add more solvent, the moles of solute, here how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's see, I have 16 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The solute does not change. The solute in both of these solutions, this is the concentrated solution and this is the dilute solution, the amount of solute doesn't change. In this little example here, I had, let's say each dot represented a mole. I had 16 moles of solute dissolved in both of the solutions. But what changed was the amount of solvent. Let's say I went from 50 mils of solvent to 100 mils of solvent. So I cut the solution in half. We can clearly see that the moles of solute are the same, but they're more dilute in the solution, right? Alright, so dilution equations, or dilution problems, they change the concentration by changing the solvent. The moles remain constant. I'm going to start with an equation knowing that that's the truth. So the moles of solutes in the concentrated solution always equal the moles of solute in the dilute solution, right? Although the moles of the solute remain constant, the molarity changes, or the molarity of the concentrated solvent is different than the molarity of the dilute solvent. The other thing that varied was the volume. If you add more solvent to a concentrated solution, you get a higher volume. So the volume of the concentrated solution is different than the volume of the dilute solution. All right. Now remember that molarity times volume, I told you in liters, molarity times volume I told you equaled moles. So if I know that the moles of the concentrated and dilute solution are equal, can't I calculate moles as molarity times volume? Yes. So for moles of concentrated solution, I can replace that with the molarity of the concentrated solution times the volume of the concentrated solution. For the moles of dilute solution, which is the same, I can change that to molarity of the dilute solution times volume of dilute solution. As the molarity of the concentrated solution is usually higher, but the volume is less. The dilute solution molarity is less. That's what it means to be dilute, lower concentration. How did it get lower? We increased the volume of the solution by increasing the solvent. So the molarity times the volume of the concentrated solution, because those are different, but they are moving in opposite directions, equals the molarity times volume of the dilute solution. This is what we call the dilution equation. If you want to change the concentration of a solution, or if you increase or decrease the concentration and want to know what volume you need to add, you're going to use the dilution equation. The dilution equation says the molarity of the concentrated solution times the volume of the concentrated solution equals the molarity of the dilute solution times the volume of the dilute solution. Now, you might have seen this in a different class written differently. Instead of concentrated and dilute, sometimes people say the first solution versus the second. M1V1 equals M2V2. This is the same exact equation. This is called the dilution equation. The initial, or you might say initial and final, okay, that's another way it's written. But you have two solutions, the initial and final, or concentrated and dilute, 1 and 2. Molarity times volume equals molarity times volume. Okay, so let's practice some problems and see how we're going to use this equation. Okay, let's see this problem here. It says, how many milliliters of a 12 molar HCl solution are needed to make 500 milliliters of a 0.1 molar HCl solution? Now, how do you know you have a dilution problem? That's actually the major problem. We know what the dilution equation is. Molarity times volume equals molarity times volume. How do we know when to use this? When do we know we have a dilution problem? Alright, what you're going to do is when you read a problem, if you have two molarities and two volumes in that problem, and there's one unknown in that problem, well, here's two molarities and two volumes, you're going to use that equation. Let's go back. It says how many milliliters? That's a volume. Okay? And it says of a 12 molar solution. That's a molarity. So we're given molarity. We're asked to find volume. It says are needed to make 500 milliliters. Wait a second. That's a volume as well. And then of a 0.1 molar solution. That's a molarity as well. So when you first read this problem, if you notice you're given two molarities of the same solute, that's going to be a dead giveaway you have a dilution problem. Because if you're given molarities of different solutes, you might have a stoichiometry problem. But molarities of the same solute tells you that they're different concentrations. What do I mean by that? Here we have two solutions of hydrochloric acid. We have the 12 molar and we have the 0.1 molar. The 12 molar is the concentrated solution because it's a higher concentration. The 0.1 molar is the dilute solution because it's a lower concentration or molarity. So here we have a concentrated HCl solution, and here we have a dilute solution of HCl. It says how many milliliters of the concentrated. So we are given the molarity of the concentrated, and we're asked to find the volume in milliliters of the concentrated. And then we're given molarity of the dilute, and we're also given the volume of the dilute solution. So we're asked to calculate volume of the concentrated. So let's rearrange for that. Molarity of dilute times volume of dilute divided by molarity of concentrated. I basically just divided both sides by molarity of the concentrated solution there. Alright, so I just did some algebra. So I rearranged to solve for our unknown. Oops, sorry. Alright, so the volume of the concentrated solution will equal the molarity of the dilute, 0.10 molar, times the volume of the dilute. The volume here is in 500 milliliters. People always wonder, should I convert that to liters? You don't need to, because the only time you need liters in the solution problems is if you're calculating molarity. And because we're not calculating molarity specifically, we have two molarities, we have two volumes. Whatever the units for one volume is will be the units for the other. So notice we're asked to calculate milliliters of our concentrated solution. We're given milliliters of concentrated solution. Those will end up being the same unit. So as long as the units are the same, use the same volume units. They can be liters or milliliters. Alright, what's the molarity of the concentrated? 12 molar. So the volume of the concentrated solution, notice I've got a molarity on top, a molarity on bottom, and I'm solving for milliliters. That's my unit left. So 0.1 times 500, that's 50, divided by 12. So it would be roughly 4 point something. So 50 divided by 12 is 4.2. So the volume of concentrated solution that I'll need is 4.2 milliliters. Now, what in the world does that mean? I always want to know, why did I just calculate that? Because when you get into a real lab, you'll know the calculation, but you won't know, maybe you've never thought about, what does that mean to use it? Here's what it means. Alright, you want to make a dilute concentrated HCl solution. So you want to make a 0.10 molar HCl solution. And let's say that your solution calls for 500 milliliters of it. What you're going to do is you're going to go grab something called a volumetric flask. You've probably seen these before. They have a marking right here, and it will say 500 milliliters right here. And it's called the volumetric because that line right there, if you fill directly the meniscus right to that line, you have exactly 500 milliliters of volume in that flask that you measure. So this is a volumetric flask. You're going to grab a 500 milliliter volumetric flask. You want to fill the thing with water and your concentrated solution. So you go grab a bottle of HCl. The stock solution, a chemist would call it. And this stock solution will be labeled 12 molar HCl, or concentrated HCl. This is as concentrated usually as you can get for hydrochloric acid. And you'll buy this from the company, concentrated as is, and you want to know how much of this solution, what volume, should you pipette out of here and put into your flask in order to make a 0.10 molar hydrochloric acid solution, because you're going to dilute it by adding water. So in this problem, it says if we want to make 500 milliliters of a 0.10 molar solution, we needed 4.2 milliliters of the concentrated solution. So I'm going to add 4.2 milliliters. That's not much out of 500, is it? Initially into my volumetric flask. That doesn't fill up to the line. That's not 500 milliliters. That's the concentrated solution. What we're going to do then is we're going to fill the rest up to the line with our solvent, which is water. And technically you should do this the reverse way because you always add acid, which means you add water and then you add acid to it. So what a real chemist would do is they would practically, so why do we do this? Because when you put water into acid, it's very exothermic in a bubble. So what you probably want to do is you're going to add a little bit of water first. You'll add about that much water. So you've got your solvent water here. You want 500 milliliters of solution, so you need to add some more. You're going to take 4.2 milliliters of your concentrated solution. That's going to begin to dissolve in there, and then you're going to add the rest up and fill the rest of the way until you get to 500 milliliters. And then, when you do that, you're going to add to there. With water, you'll have a dilute solution instead of concentrated. So that's what you do. You add 4.2 milliliters of water and you fill the rest of it up, your HCl solution, and you fill the rest of it with water, and you have a nice dilute solution. This is how chemists make different solutions from a stock solution, all those different concentrations. We use the dilution equation. Molarity times volume equals molarity times volume.